and welcome back. So this is the third video that I would add as a revision, and if you just look at some examples we are going to be taking, and I'm going to be quick, because this is a revision, so it's not the teaching part. I already did the teaching part. So there are going to be shortcuts. I'm going to be explaining without writing a lot of the details. So you need to study before going through this review, just to make sure that you understand and you're following up to what I'm trying to explain. So here, for example, there's a case study, and here I'm just looking at the case studies that we can take. In this case, there are many case studies that we can go through. And now, what are the key equations that you need in these case studies? Well, when you're going to be in the exam, I'm going to give you a group of equations. One of those sheets is the low pass filter, the high pass filter equation. And of course, you need to remember that FC, which is the cutoff frequency, is equal to 1 divided by 2 pi RC. Okay, so you need to remember that. Wheatstone bridge, so this is the Wheatstone bridge, where you're going to have the voltage supply to that equation there. There's another equation as well which looks similar to this. I can supply that to you. The RTD, so there's another equation for RTD. For the RT, the new resistance changes. The resistance changes based on the difference on the difference in temperatures and on the coefficient. We have the thermistor, which is the exponential term. In this case, if you can recall, I'll just make it exponential clearly. So this is like the exponential term. So B is a constant, and T naught to T, that's the change in the temperature, and that is the initial resistance, and this is the final resistance. The piezoelectric sensor, of course, the volts go to the distance into the stress, which is force over area, that is the pressure. So these are like some kind of equations. So if we look at the equation, for example, we looked at last time, but the low pass filter having cutoff frequency. So we have FC, the input voltage, we have Vn, we have the signal frequency, which is 500 hertz, and we have calculate the output voltage. So the output voltage will be V out divided by Vn, if you can recall. So the equation was more like that, if you want to put it. So it was V out divided by Vn is equal to 1 divided by 1 plus F over Fc to the power 0.5. I think I missed something here. It was to the power 0.5, the equation. I don't know why this thing missed it here, but I'll just show it to you. Okay, so yes, it is. You can see 1 over F over Fc to the power 2, and then that is all, the whole thing to the power 0.5. So that is the correct equation, and we already solved this last time. So let's see another problem just for the high pass filter, where, for example, here we find the critical frequency for which a 120 hertz signal. Now this is a low frequency, and we want to get rid of it. Has an output input voltage ratio. So we have the voltage ratio is 0.01. If you substitute V out over Vn, which is 0.01, we're going to find FC. Now FC is found out to be 12 kilohertz. That is the cutoff frequency. And when we say cutoff frequency for a high pass filter, that means it will pass the high frequencies, and it will cut off the lower frequencies. So anything lower than 12 kilohertz will be cut off. In this case, Fc is equal to 1 divided by 2 pi RC, and if we substitute C as 0.01 microfarad, and then we can calculate what is the value of R. So here we can calculate, we are identifying, we are designing what are the values of C and R to obtain that 12 kilohertz. Now, if we are getting now a 30 kilohertz signal, and this 30 kilohertz signal has a 120 so we want to see a 30 kilohertz signal which is a high pass filter. Now I'm guessing that this 30 kilohertz should pass by because 12 kilohertz it is the cutoff frequency. So when you substitute 30 divided by 12, you find out that 93% passed, which means this is good somehow, yani, but we are losing about 7% of that signal. Okay, so this is something that we would consider as well in this case. Okay, so this is the solution for 217. So now I'm having an idea. I'm just giving you the ideas that we can solve in this case. Now let's look at, for example, the Wheaton bridge. Now Wheaton bridge, we already know the Wheaton bridge. Just make sure that the ratios, you get them correctly. And because if you have the ratios correctly, you have the null voltage, which is equal to 0. But as we said that the null voltage will not be equal to 0. In this case, it will have a certain kind of a voltage. Why? Because the resistance changed due to the change in temperature, for example. Okay. In this case, this is like just a direct substitution. I have R1, R2, R3, R4, and you're going to substitute it in this equation, in which you're going to find the answer. Now, going back, looking at the Wheaton bridge. So the Wheaton bridge, this is the one that we have here, and that is the other form of equation, which is exactly like that one, just rearranging it in a different way. So if you have these 4 resistors, you're just substituting. Now take care that I'm going to tell you that the RTD changed, which makes this Wheaton bridge unbalanced, which when I say unbalanced, that means the null voltage is not equal to 0, as this delta V will be changing. Okay, so just consider that as one of the things that will be considered when we do our calculations. Okay, good. So going back, now this is like a problem where a strain gauge is placed in a Wheaton bridge. Now instead of saying that I have an RTD, now I'm having the change in resistance is because of the strain gauge. As we said, the strain gauge, which is used to measure the pressure, and when I am applying a pressure, the resistance changes because of the strain, which changed the structure somehow of the material. So what do we have? For a 10 volt supply, design the bridge so that the resistance changes from 120 to 121 ohms. Okay, so that is a really very small change, and this is why they are using a Wheaton bridge, because it can identify the small resistance changes. And so here says resistance changes from 120 to 121 ohms to produce an output voltage difference of at least 0.1 volts. So here we are saying that this is the delta V that I'm going to have. Now looking at this equation, what do I have? At 120 ohms, I should have everything to be nulled, to be 0. And on 120 ohms, I'm going to have a change. Okay, I'm going to have a change. So this is just to have this kind of change, which will give me 0.1 volts. Now the steps here, without showing the problem, V out, in which I already showed you the equation, which is this equation at the top here. And then we are going to select R1, R2, and R3, and R4. So we are going to select the suitable resistors. And of course, one of those R4s is that 120 ohms. And somehow I'm selecting the resistors to obtain a 0.1 volt. And so this is the idea of how I'm going to do it. Now 0.1 volts, if we feel that it is a bit low, then we need to add an amplification. So we are going to select these to amplify the small resistance change effectively. So this is what you're going to do. Now the RTD, we are using this equation. RT is equal to R0 into 1 plus alpha delta T. Again, the delta T, I think this is similar to the problem, which is 50 minus 0. And I'm giving the value of alpha. This is the R0. I substitute. And I'll give RT. I think this is simple. Let's go to the next problem. Now, having an RTD used to monitor temperature in a chemical reactor. And now why we call it case study, because we want to put it in a case study. So you have a chemical reactor, which means a reactor that has a reaction. And the reaction is chemical. The sensor outputs a resistance change from 100 to 150 ohms. Now what we are trying to measure the temperature in the chemical reactor. When the temperature changed, the RTD changed, which I mean the resistance, which is the resistance temperature detector, resistance started changed from 100 to 150 ohms. Good, so I have R0 and I have RT, the final resistance, for the temperature change of 0 to 200. Now the only thing that I don't have here is the alpha. So I need to know what is the material that I have for RTD, so that I know what is the thermal coefficient. So I would guess that I have this information. Design a signal conditioning circuit to convert this to a voltage signal. Now, to convert it to a voltage signal, I have two things here. First, I think this is simple, but because what do we have? We have the output, which is 0 to 10 volts, which is V1 and V2 in this case, and I have the input values. The input values that I have, now you may get confused, are the input values 0 to and 200, which is X1 and X2, or 100 and 550 ohms is X1 and X2. In this case, remember that what is the case of what are the transfer functions that I'm having in this case. So for me, that I have a group of blocks, and I need to know these group of blocks that I have, what do they represent. So in this case, for example, I have here a group of blocks, and these group of blocks that I have, what I'm trying to say is that I have a transfer function. I need to remove this. So I have a transfer function here, but what is this transfer function and what is happening? Let's try to be more accurate. So I have a temperature change, and this temperature change using the RTD is I'm having a temperature change T2 resistance, right? So this is what I'm having, and then I'm having resistance to voltage, and that is the second part. What I'm having resistance into voltage. Here it shows me, and let me go back. So the resistance change, it depends on the equation where RT is equal to R0 into 1 plus the alpha. Let me extend this. So I have here 1 plus alpha, that is that is multiplied by delta T. Now when I find what is RT, I can convert it into voltage. Which means here in this case, now I can just explain it again. So the RTD I can calculate the final resistance, in this case I already gave you the final resistance, but I can calculate the final resistance. So I have R1 and R2 in this case, which are ready. Now what is converted to voltage? The thing which is converted to voltage is the resistance, not the temperature. So now R1 and R2 are the X1 and X2, and the 0 and 10 volts are the Y1 and Y2. Okay, so I hope that you got the idea. And of course, you have many different ideas if you want to design that system. Here it says you use a voltage divider to convert resistance to voltage. Now I can use a voltage divider or a Wheatstone bridge so that I can convert resistance to voltage. So this is the idea if I want to design for my case study. And then I can amplify the signal if I feel that the output voltage is very high. So I need maybe an operation amplifier. And remember that operation amplifiers is I take the resistance ratio so that I can identify the amplification, the amount or the amplitude or the amount of the amplification. Okay, so I hope this is clearer to you of how this is reflected in a design way. Okay, good. Going back to the thermistor. So the thermistor, we have a thermal resistance. Now the thermistor uses what? Uses this exponential term. So I have a thermistor of R naught at T naught and a B, which is the material constant of 4000. Calculate the resistance at T1. So that I already have what? I already have 1 over T minus 1 over T naught. So I have T naught, I have T, I have B, I have R naught, which is 10 kilo ohms. I'm going to calculate the final number of ohms. So it was 10 and it became 6,000 kilo 6,000 ohms, which means that you can see that it is like it's multiplied by 600 times by changing the temperature from 25 to 100. So imagine how much the resistance increased because of the change in the temperature. And remember that for the thermistors, we have the semiconductors in which it can increase with the increase in resistance, or it can decrease with the increase in the resistance. So both, it depends on now what kind of a material I'm selecting that identifies that relationship. Okay, so this is just an example that you can use a thermistor, which can be anywhere in a fridge, for example. Here just it gives you an example as a case study, but I would like to go to a more of a problem to be solved. I think so we already solved this problem before, and I'm not sure if I solved this problem, so let me solve it with you. Okay, so so what do we have here? We have I'm just fixing some stuff here. Sorry for that. Okay, great. Now capacitance level sensor. Capacitance level sensor. So now we know the capacitance level sensor uses this equations. C is equal to ER, which is the dielectric constant, into E naught, into area divided by D. We have area is equal to 1 centimeter square. Okay. And we have the D, the distance between the two plates is 1 millimeter. So we just convert that to centimeter. So we have A divided by D. And have we ER, the dielectric constant, which is 2.5. So we are going to substitute 2.5. Calculate the capacity when the tank is half full of water. R is equal to 80. Now, is it 2.5 or 80? Now that's confusing. We need to have only one value, not two values. So let's see the solution to understand which value did he use. I think he used the one which is down there. That is 80 times E naught, which is 8.854. I'm going to fix this. Okay, so I'm going to call this E naught 8.854 into 10 to the power minus 12. So I'm going to take this just to make it neat. Sorry for this. So this is what I have, and then I'm going to multiply it by area. In this case, the area is 1 into 10 to the power minus 4. If I change this centimeter square to meter square, and then divided by D, if I change it to meter, it will be 1 into 10 to the power minus 3. Okay, 10 to the power minus 3, and we will have the answer is going to 7.08 pico, whatever it's called, farad. Okay, so that's what we have here. Now this is for the examples as you have seen. Now I want to go more to the conceptual understanding, or some critical thinking questions. Going to that, I'm going to finish this video. I'm going to stop it now. I'm going to have a fourth video for you. Okay, thank you very much.